Very good. Let's see. In today's class, I want to discuss the introduction of entropy in the hands of Rudolf Clausius. So let me remind you of what it is that we had been doing last class. We had seen that the Carnot's principle can be reformulated in terms of the efficiencies. So the idea here was that the efficiency of any engine, let's call it E prime, it has to be less or equal than the efficiency of a reversible engine that's operating between the same two temperatures. So on the one side, here we have, this is the amount of work divided by the input heat, and we can write it as work is the amount of heat you get from the high temperature reservoir, subtract the amount of heat discharged into the low temperature reservoir, divided by Q1. And this is supposed to be less or equal to 1 minus T2 over T1 when T is the Kelvin temperature. Anyway, so this can be rearranged into the following inequality. The amount of heat input at T temperature T1 plus the amount of heat input Q2, capital Q2 is minus lowercase q2. This has to be less than 0. So let us focus on what's going on in this with this engine when we have an equality sign. What we saw when we have an equality sign is that all the heat Q1 happens at temperature, enters at temperature T1 and enters heat Q2. So this is Q1 and heat Q2 is delivered, negative heat Q2 is delivered to the engine at temperature Q2. No heat transfer occurs on the other parts of the cycle. So this is the Carnot cycle. So these curves here are isotherms, and those curves there are the adiabats, no heat. Adiabats. Here we have Q equals 0, and isotherms means T equals constant. Very good. This, if you follow this path reversibly, then you get the equal sign. Because if the path is reversible, then E prime is also 1 minus T2 over T1, right? So you get the equality. Very good. What I would like to do now is first mention a little bit better what we mean by reversibility, and second, try to generalize these processes, these cycles, to more general shapes. First, please notice that when we have something like a graph like that, the axis would be things like pressure and volume. So what we mean by a point in this space, it's what we mean by that is really a macro state, a state of the system that is described by purely macroscopic variables like pressure, volume, temperature, number of particles. So because you have had previous courses on statistical mechanics, you probably know that a point in such a space really reflects a situation of thermal equilibrium described by a Boltzmann distribution or a Gibbs distribution. Same thing, basically. So the crucial thing is that this describes a macro state, a state described purely in terms of macroscopic variables. So instead of describing the system by giving all the 10 to the 23 variables that describe position and momentum, so you describe the system in all its microscopic detail. So 10 to the 23 P's and Q's. We are going to often describe the system in terms of a macro state, and we have half a dozen macroscopic variables. So this distinction between the microstate and the macrostate is absolutely crucial. You do not know the microstate, and please notice how I'm starting to use notions of some information theory or lack of complete information. Since you do not know the exact microstate, you start describing the system in terms of macrostates. This allows us to consider two types of reversibility. One is what's called microscopic reversibility, which amounts to taking the coordinates and the momenta and flipping them into the same coordinates, and you flip the momenta. So if these are vectors, you keep the positions the same and you just flip the direction of the momenta. So here, when you perform this transformation, you reverse the motion. So for example, when people talk about the time reversal invariance of the fundamental equations of physics, that time reversal refers exactly to this transformation in which you change P to minus P. The other type of reversibility is called Carnot or thermodynamic reversibility, and it refers to retracing in the space of macro states. For example, here you can take a process that takes you from one state to the other, and you can go in one direction or in the other direction. What this means is that you retrace your steps and recover the same macro states, but in the opposite order. Please notice that that does not mean that you have flipped the velocities of the particles. So these two types of reversibility are very, very different. Here, you're just retracing your steps, but the molecules can be doing whatever they want. While here, you really are talking about reversing the microscopic trajectories. So when people talk about thermodynamics induces an arrow of time and it breaks the reversibility of the fundamental equations of motion, that's complete nonsense. Do you appreciate that we're talking the time reversal invariance of the equations of motion has to do with microscopic reversibility, while thermodynamics is always concerned with Carnot reversibility. They are completely separate issues. There is yet a third type of reversibility, which is also called recoverability. which refers to being able to go from one state to the other by any means whatsoever. You just, if you are going to go from A to B, then there is the possibility of, by any means whatsoever, coming back, going from B to A, quite irrespective. So these are supposed to be reversible, all states of equilibrium, right? The intermediate states in the Carnot situation are supposed to be all states of equilibrium. So I should write here macro states of equilibrium. In this other situation, you are going to go go from B to A by whatever means possible. It doesn't have to be reversible. And this we're not going to be using these notions so much. This is more associated to the name of Planck. Very good. Now that we have talked about a little bit what we mean by reversibility, meaning you take your system from equilibrium, you follow a path, and then you're capable of doing precisely the opposite direction. The only way you're going to be able to do that and go from a situation of equilibrium to equilibrium to equilibrium to equilibrium is if you do it very, very slowly. So the idea here is that these paths are traversed, reversible paths are traversed infinitely slowly, so that the system is as close to equilibrium as is possible. Very good. So now let us generalize. What we want to generalize the following. This statement here, we want to generalize it. And the way we're going to generalize it is by saying, look, the equality sign corresponds to a reversible cycle of the type that we drawn there. So I would like to draw more general reversible cycles. We're also going to focus on the equal sign and say, look, suppose that here I'm going to draw the isotherms. So if this is PV, remember how the isotherms work? For example, for an ideal gas, we have PV is equal to NKT. So constant T means P is 1 over V, so we get these hyperbolas. The adiabats are curves that go steeper. Adiabats, this is no heat exchange, something like that. Very good. So now I'm going to draw an interesting cycle here. I'll do it in red so that you can see it a little bit better. I'm going to say, look, I'm going to use this cycle that follows this path there, and then it comes down, and then it goes here, and then it goes there, then it comes back up again, and then here, and then there. So the cycle is something that has that funny shape. So here, let me see. Suppose I put heat Q1 at temperature. I better just put it here at temperature T1. Then heat Q2 at temperature T2. Then heat Q3 at temperature T3. Finally, heat Q4 at temperature T4. So now let's write out what kind of inequality we could get in this situation. Well, we could say, let us consider the quantity Q1 over T1 plus Q4 over T4. That is those are the quantities that would correspond to this part of the diagram in which you close it down here. So imagine just that Carnot cycle. Then we have the other piece, which is Q2 over T2 plus Q3 over T3. That corresponds to this part of the Carnot cycle. So what can we tell about all of these quantities here? Well, this one, by Carnot's principle, is negative, right? If you just follow this reversibly, right? So this is a reversible cycle. If you just compute from here, you're going to get that that is negative. If you just compute the other component here, you're going to find out that this is negative. So if you're adding two negative numbers, this is going to be negative. In fact, the way I should say it is, if this is done reversibly, this is 0 and that is 0. And so this is going to give you a 0. If the path is done irreversibly, like for example, I do it quickly, right? Then this part is going to be negative. If this is done quickly, it's going to be negative. So I can build an identity like that, so that in general, when you have heat absorbed from thermal reservoirs, heat reservoirs at temperature T1, this quantity is going to be less or equal to 0. Okay, the next crucial development in all of this is to recognize that any sort of, if you just draw the slivers that go with, well, this is difficult to draw, but any kind of generic cycle there done reversibly is going to lead to draw your adiabats, and for each sliver you can write down an equation of this type here. So what this leads is to an expression for what happens as you have infinitesimal a generic cycle expressed in terms of infinitesimally thin Carnot cycles. This is going to give you equal to 0 if it's done reversibly. If it is not reversibly traversed, then you're going to get less than 0. So this is what Clausius did in 1865. And the genius consists in actually seeing the potential of such a construction. Because if going around the path is gives you something that is 0, so consider a reversible path, reversible paths, then you're going to have dq over t equal to 0. So if you can rewrite this as saying, if you go from A to B by a reversible path, and you go from A to B by another reversible path, R1 and R2, then going from A to B along path 1, dqt is equal to going from A to B along path 2 of dq over t. Okay, so if you're going to go around it, so you go from A to B and then B to A, that's 0. But that tells you that going from A to B along one path or the other have to be equal. Of course, if you retrace this one, you're going to get minus that one, and you get it. Very good. So what this means is that the integral along along a path is actually independent of the path. So this means that integral is independent of the path, provided it is reversible. So provided it is reversible. So what Clausius realized is that this allows you to invent a function. So the function would be the entropy. This function at the point B can be written as the function at the point A integrate with an additional, the difference in entropies between the two. This is the integral from A to B of dq over t. So because it doesn't matter what path you follow, if I give you this constant of integration here at A, I integrate along any path and it gives me the value at B. So this is what allows us to define the notion of entropy. Very good. Let me see. What I want to say now is the following. The interesting thing about this quantity is that by now we're no longer talking about cyclic processes. Whatever this quantity is something that may be made to refer to a path that does not necessarily close. Going from A to B, you get the difference here between the two entropies of those 2 points. And so what, right? The so what, and the reason that this actually is important is that if now we consider a more general situation, consider irreversible path. Irreversible path. So consider a process that cannot be truly reversed because it's done too fast. Under those circumstances, imagine that you go from A to B along an irreversible path. Please notice how I've drawn it as a dashed line here. And the reason is the actual path from A to B is not something that's happening on this space that I drew here, which is a space of equilibrium macro states, right? It's flying through other dimensions in going from A to B. It may very well be, for example, that this path is happening, this process is happening so fast that one part of the system is hot, another is cold, there is turbulence, the densities are not constant, it's a mess, right? Okay, that's what I mean by an irreversible path. So suppose you go from A to B and then you return by a reversible path. Under those circumstances, we can say the, okay, let me draw it like here. For this particular path, that cycle that is irreversible along one chunk and then reversible along the other. In this case, we're going to have that this is less or equal to 0. Now, what does dq mean here? Well, dq means dq is the heat provided by the reservoirs at the temperature T. T is the temperature of the reservoirs. So this is the T of the thermal bath. Right? So that's why computing a quantity like this makes sense even when the system is undergoing an irreversible process. This is the amount, just check the reservoirs, how much heat they're providing, divide by the temperature, proceed. In this case, we can actually separate the there. Separate the path along the cycle along two pieces. One of them is this one, and then the other one is A to B along the reversible path. So it doesn't matter what the path there really is. Sorry, not from A to B, from B to A. So I go from A to B irreversibly and then return from B to A back reversibly. And this is supposed to be negative. Now, from what we saw before, that piece, here we are, from A to B is SB minus SA, right? SB minus SA when you go from A to B. In this case, we have B to A. So this is SA minus SB. Very good. How about the other piece? This piece here. We cannot say what this represents for the entropy of the system that's undergoing irreversible paths. Entropies are only defined for equilibrium states. But we can actually look at this and realize that, hey, this is the amount of heat supplied by a reservoir at temperature T. The entropy of the reservoirs change by, if this is supplied, it's a heat that the reservoir lost, and therefore as far as the reservoirs go, this is negative. So let me write here that minus dq is the amount of heat supplied to the reservoir. dq is the amount of heat supplied to the system minus dq. So the quantity that we have here is minus the change in the entropies of the reservoirs. So this is change of the entropies of the reservoirs, change here. And since this would be the change B minus A, because, well, it's B minus A, because of the minus dq there, I should write this as A, well, as B minus A plus this other piece. This is negative. Let me collect terms here, and what I have here is SB, yes, let me just write it out. SB is a reservoir plus SA minus SB reservoir plus SB is less or equal to 0, or as if we call this as total, the entropy of the system plus the reservoir at A, in the states A, in the initial state, and this is SB total, what we conclude is that the final entropy get this guy onto the other side is bigger than the initial entropy. And this is the statement of the second law of thermodynamics. By Clausius. Quite remarkable. Let's talk a little bit about it. First thing, okay, so this is what allowed Clausius to make these amazing statements. The energy of the universe is constant. The entropy of the universe increases. The first and the second law. This is very nice. It's the kind of thing you would like to write on a T-shirt, but you have to be extremely cautious. First, we now it was fine when Clausius made these statements back in 1865, but you have to be very careful here, because now we know much better. We know, for example, that the universe is expanding. Space is curved. Space-time is curved. The universe is expanding, and so the problem is. So this statement here is rigorously wrong. In fact, I wouldn't say rigorously wrong. It's not that the energy of the universe is decreasing, or that the energy of the universe is increasing. No, the statement is actually meaningless, because the energy of the universe is not a quantity that can be unambiguously defined. Whenever you have curved spacetimes, it is not possible to actually add the energy in one region of space-time with the energy in another region and add them to figure out the total. You can't do that. So the statement, the energy of the universe is constant, is just meaningless. How about the entropy of the universe increases? That's also not quite right. And the reason is that if you look at the way we actually did all of this, when we look at this expression here, the entropy of a system is only defined in situations of equilibrium. And if there is one thing that we now know about the universe, is that the universe is not in equilibrium. It's expanding. So again, it's not that the entropy of the universe is increasing or not increasing. The entropy of the universe is not defined, or at least the thermodynamic entropy of the universe is not defined, because the universe is not in equilibrium. So you have to be very cautious about glib pronouncements of that type, and people do it all the time. So you have to realize that they don't mean much. It's better just to keep quiet. That, of course, does not detract from Clausius' big accomplishment. It's interesting that despite all that, he did not achieve that much fame. I mean, it's very difficult to imagine coming up with something more important than the second law of thermodynamics, right? So, of course, we know him. We know his name. He's famous. Blah blah blah. But in his own time, he wasn't really that famous. This was a time. This was a time, 1860s, 70s, 80s, when there was an incredible amount of rivalry between the various countries in Europe. And so Clausius was German. The Austrians did not really want to give him too much credit because Boltzmann was working on these topics. The English did not want to give him too much credit because, after all, Maxwell was working on these topics, and Kelvin. So they didn't want to admit that this guy had done something tremendously great. They just wanted to use it. The French, okay, yes, everything started with Carnot. Carnot knew everything. So how? In any case, when they actually had this guy, this poor guy dies, Clausius, and they had to come up with funerals and stuff, and they needed to write an obituary and explain everything. Nobody wanted to do it. So in order to get someone to do the obituary, they had to appeal to somebody who really was coming from the third world, from the United States. So they had to ask Gibbs to do it, and of course he did it. So, but it's an interesting story of how science in those days, and to some extent today too, is so affected by considerations of nationality. Okay, let me see. Clausius. Yes, Clausius did another thing that was kind of very important at the time. He started attempting to explain the second law of thermodynamics from mechanics. So for Clausius, the second law was an absolute law. It wasn't a matter of extreme probability that the entropy would increase. It was an absolute law. Was absolute, and so he attempted to derive it from mechanical principles. So by absolute, what I mean is that the second law was a matter of certainty. There could be absolutely no violations of the second law, and therefore derivable from mechanics. He attempted to derive it, and of course he failed. Very good. The next person we want to talk about here is Maxwell. Maxwell's big contribution in this subject was the introduction of probability into physics. Clausius introduced the notion of entropy, and Maxwell introduced the notion of probability. He was probably inspired, so this was done around 1860. Please notice it's more or less around the same time he was working on electromagnetism and coming up with his first papers on Maxwell's equations. So clearly the guy was being very creative in these years. Around 1860, he introduced the notion of probability to discuss what happens if you have a gas and you have all of these atoms. Clearly, you're not going to be able to know precisely the position and momentum of every atom there. So you introduce the notion of probability, the notion of probabilistic methods to even reason about these problems, to account for the fact that you have very limited information. he was probably inspired by a previous piece of research of his in which he was studying the rings of Saturn. He wanted to explain the rings of Saturn, the orbits, as orbits of chunks of rock, ice going around Saturn. And of course, you could not keep track of all the initial positions and velocities of those chunks of ice going around Saturn. And so he started thinking of introducing probabilistic methods there. Eventually, he succeeded in dealing with ideal gases. And he came up with the notion of a distribution of velocities. And his conclusion was that the number of molecules in a small range of velocities was going to be proportional to the square of the velocities d3v. So his conclusion was that, let me read it here. He said something like, yes, that velocities are distributed among the particles according to the same law as the errors are distributed in the theory of the method of least squares. So previously, probabilities had been introduced by Gauss and Laplace to discuss errors, experimental errors. Now probabilities are being introduced to discuss fundamental physics. That's the big difference. But what do we mean by the distribution? Okay, what do we mean by probability? We're going to see this theme repeat itself over and over and over again. People use the term probability, without really knowing what it is that they're talking about. So Maxwell had two definitions of probability. One of them was fraction of particles, of the total number, capital N, of particles in the gas, the fraction with velocities, the fraction with velocities in d3v. So you can see that this is a kind of like a frequentist interpretation of probability. On the other hand, if it is the fraction of velocities in d3v, you can see that this interpretation is frequentist, and also it's kind of a property of the gas. It's a mechanical property. So this distribution then, or this probability interpreted in this way, this is a mechanical property. That's amazing, because if it is a mechanical property, you should be able to derive these distributions purely from mechanics, like Clausius would have said. On the other hand, Maxwell knew that this distribution was obtained, or he derived it, making fully certain, making emphasis on the fact that you were doing these quantities because you have very, very incomplete information. So you see that the two aspects of probability, one, that it allows you to figure out stuff about the real world, or at least according to the frequentists, and the fact that they arise when you have incomplete information, was actually very, very clear in his mind. In the lecture notes, I actually give an argument by Maxwell of 1860 as to how you can derive this probability distribution. And what's very interesting about this argument is that he was not using arguments from mechanics. He was using symmetry principles, the kind of principle that you really use in order to derive probabilities that arise from incomplete information. So he had both of these ideas in mind. He was very, he actually was very aware that the second law, because you have probabilities, the second law is not absolute, is true, or is highly probable. It's true improbability that it's, he would say, that has only statistical certainty. That violations of the second law are possible, only extremely unlikely. Side remark. Okay. If you want to see violations of the second law, they need not be very, very unlikely. Just open the window, look out, the sky is blue. The situation of maximum entropy, the entropy of the universe increases until you reach a maximum. The situation of maximum entropy is one in which the density of the air is completely uniform, right? On the other hand, once you do things properly, you're going to realize that the density of air actually has fluctuations. These fluctuations represent lower situations of lower entropy, right? A little bit lower entropy every time you have a little fluctuation. And when light scatters off these fluctuations, that's when you see the blue sky. So if you want to see instances of microscopic violations of the second law that are going on absolutely everywhere, just look out for the sky being blue. That's one of these phenomena that arises from fluctuations. It was only Einstein that started like really looking at the fluctuations, deviations from the maximum entropy as being really interesting phenomena that could tell us a lot about what's going on at the microscopic level. But that's for later. Anyway, after that aside, let me see. Maxwell was aware, because of his understanding, or rather the partial understanding he had of probability, that the second law has only statistical certainty. Fluctuations and small violations were possible. And there was another interesting connection, is that when I said here, on the one hand, you have this idea of probability as being the fraction of molecules with velocities in D3V, which is sort of frequentist. He also was very aware that he was dealing with a situation of incomplete information. How did he know that? Or how did he reason about these things? Well, in 1867, he proposed in a letter the following situation. Suppose that you have a gas in two compartments with a little hole, and the little hole, you cover it with a door, and you have this daemon. Here's the daemon. There's the daemon. And the daemon does the following. Here you have a gas, and let us assume that you have the gas at temperature T1 on the left and temperature T2 on the right, in such a way that the temperature T1 is bigger than T2. So what the daemon does is, when he sees a molecule with high temperature going from, high energy, high velocity going from the left, he opens the door and lets it pass. So this is high velocity. And then he does the following, and then he closes the door. And then he does the same thing when there is a slow molecule going from the other side. So you can see that every time a high molecule comes from one side, he lets it through. Every time a slow molecule goes from the other side, he lets it through. And the net result is that you have a transfer of heat going from low temperature to high temperature. So the Maxwell daemon can violate the second law and make heat flow from low temperature to high temperature. Very interesting. So this is the Maxwell daemon. The crucial element here is that the daemon has to know when the particle has high velocity or slow velocity. So it is a matter of information. The daemon must have information, microscopic information, which is precisely what we do not have. So the reason there is a second law for us is that we do not have this information. Should the daemon have that information, you would be able to violate the second law. Can you make, instead of having a daemon, could you make a little machine that sort of like operates in such a way that does this? Remarkably, you can sort of do that, but not for very long, because your little machine at some point is going to reach thermal equilibrium with the two baths here, and so eventually everything will just, the daemon will, the little machine is going to stop operating properly. It's going to be itself subject to fluctuations, and so the whole thing will not last for very long. So it is really it's a matter of having information. You cannot really replicate this with a little machine. Very good. Next stage in this development is Gibbs. So far, we have been looking at processes in which you allow for the transfer of heat from one body to another. Heat flows from hot to cold, eventually perhaps reaching some kind of overall thermal equilibrium. So what Gibbs did, he allowed the whole of thermodynamics to be generalized beyond just transfers of heat to exchange of particles. This is what's called open systems. You do not just exchange heat, you exchange particles as well, and this allows you to handle inhomogeneous systems. For example, if you have a gas and a liquid in equilibrium with each other, clearly the system is inhomogeneous, high density, low density, and you would like to study the equilibrium between phases, and so clearly particles will flow from the liquid to the vapor or vice versa until equilibrium is achieved. So the methods of Gibbs allow to tackle this new kind of problem by introducing something similar, a quantity, a concept similar to temperature. Temperature regulates the transfer of heat from hot to cold, right? And when in equilibrium, the transfer stops and you have the two temperatures being the same. What Gibbs did was he introduced the notion of something very, very similar to temperature, the chemical potential, that regulates the flow of particles. And we're going to be seeing this in full detail later. But what this means is that by 1878, basic classical thermodynamics was completely formulated in its essentially final form. Very good. One of the things that Gibbs did that was very interesting is he was the guy who really started to understand the distinction between micro states and macro states. And he actually, well, started understanding the distinction between microscopic reversibility and macroscopic or Carnot reversibility. And so, for example, he started asking questions like this. If you have two gases, gas A, well, you have O2 in this box, and you have N2 in that box, and now you allow to mix the two, then clearly the entropy increases. The molecules of O2 that were confined to a small space, now they're in a much bigger space, their entropy increases. The molecules of N2 are now in a bigger space, the entropy also increases. So S increases in such a process. But what happens if you were to have the two components being made of the same gas? Clearly the molecules of O2 that were over there now can occupy a much bigger space, while the molecules of O2 over here can now occupy a much bigger state. What happens with the entropy? Does it increase or does it decrease? This is what is this kind of problem is what's typically called the Gibbs paradox. How is it? Because what Gibbs correctly argued was that now, in this case, if you remove the partition, the gas is going to be, of course, the molecules have bigger volume to move around, but the gas is, the entropy of the full gas is not going to be larger. It's going to be exactly the same. So how can that be? And the reason that the argument that Gibbs provided was to say, no, look, you shouldn't be confused between the actual micro states that really have now a greater volume to move around. What really matters is the entropy being a property of the macro state. It's a property of the fact that we are, and let me see, I can read, by a thermodynamic state, he wrote, we do not mean a state in which each particle should occupy more or less exactly the same position as in any previous epoch. So you're not concerned with the irreversibility by changing the position, the state of the particles themselves, but only a state which shall be indistinguishable from the previous one in its sensible properties, namely its observable macroscopic properties, such as pressure volume. So he was very aware that the entropy is a property of the macro state. He was also, so let me write it like this, S is a property of the macro state. He was also very aware that, and agreed with Maxwell, that the second law was a matter of high probability. And that it had to do with the information available. I mean, when he says it's a state which, yes, let me continue, but only a state, a macro state, shall be indistinguishable from the previous one in its sensible properties. It is two states of systems thus incompletely defined that the problems of thermodynamics relate. So clearly the states are of such, they're such that you have incomplete information. So let me see. To conclude here, what is interesting about Gibbs and Maxwell is that even though they understood that the entropy was a concept that had to do with incomplete information and that you needed probabilities to account for it, they never drew the distinction between probability, or they never came up with a connection between probability and entropy. The person who did that was Boltzmann, and to that we direct our attention in the second part of this lecture.